Hi, good morning my dear students and welcome to the World Electronics. Our activity for today will be focused on Lesson 3 of Module 2 under ALX 111, which is Electronic Devices, Instruments and Circuits. And this lesson is all about inductors. But before we proceed to this lesson, allow me first to add something important with regards to the past lesson, and that was all about capacitors. You have learned, class, that there are several types of fixed capacitors, but they differ in accordance to their performances. In terms of applicability or reliability, stability, and temperature coefficient. You have learned, class, that the maximum capacitance for these capacitors here is 10,000 microfarad, and the working voltage maximum dielectric strength or the maximum working voltage is only 650 volts. Although the capacitance is a little bit higher since it reaches to 10,000 microfarad, but the working voltage maximum voltage is only 650 volts and a minimum of 6.3 volts. The capacitance is 10 microfarad and a minimum of 0.5 microfarad. These capacitors are best applicable to filtering process in a rectifier circuits. This is to avoid harm to your amplifier unit, for example, or to television receiver. So pulsation of DC will be smoothed out by this capacitance because filtering process needs a little bit higher capacitance. Let us say 1000 microfarad to 2200 microfarad. Unlike these capacitance here, which are lower. Because these non-polarized capacitors, their capacitance may reach only up to 0.5 microfarad and the minimum is 1 picofarad, which is not applicable for filtering process. No? But another type of electrolytic capacitor, which is super or ultra capacitor, contains the highest capacitance because it reaches to 1 million microfarad. As it is labeled here, it is 1 farad. No, 1 farad. When we convert 1 farad as a basic unit for capacitance, because farad is a basic unit for capacitance, which is equivalent to 10 raised to the power of 0, like ohms for resistance, volt for voltage, ampere for current, hertz for frequency, seconds for time, Henry for inductance. Those are basic units which are equivalent to 1 or 10 raised to the power of 0. No? So when you convert 1 farad to 1 microfarad, remember micro as a prefix unit is equivalent to 10 raised to the power of negative 6. The difference between them is 6. But we are converting larger because 0 is larger than negative 6. So how many places? 6 places. For the gap is 6. So we have to move the decimal point to the right. 6 places. 1, 2, 3, 4, 5, 6. So it is 1 million microfarad compared to these electrolytic capacitors which are made of aluminum and oil impregnated, even tantalum. The maximum capacitance is only 10,000 compared to this as 1 million microfarad. No? But the working voltage is somewhere only at 2.5 to 2.7 volts. The application of this capacitor, because it is best applicable as a secondary power supply of a UPS unit for the computer system. Uninterrupted power supply. It serves as a secondary power supply because of its high capacitance, it can hold the stored voltage for a long period of time, no, around 10 seconds. Because this one, a fraction only of a second. Because once there are loads across to these terminals, the voltage stored will not stay longer, just a fraction of a second. Okay? But we have also here a silver mica capacitor, which is best applicable for radio frequency circuits. No? For the very high frequency, ultra high frequency, and super high frequencies. The radio frequencies used by the cellular phones, satellite communication, television communications. So, radio frequencies are critical when it comes to increase and decrease of temperature? Because the answer of that is this capacitor, wherein the insulator is made of mica and the conducting plates are made of silver. They are very stable despite of the changes of temperature. The capacitance is stable. They respond better to the increase and decrease of temperature. Kaya, it is best applicable. Although it is a little bit expensive, as what we have here also for the super ultra capacitor, because this capacitor, the price will be probably somewhere at 200 to 500 pesos. No? Compared to this one, which is only around 50 to 80 pesos. Remember that there's a big difference between these two. Because these capacitors here, except this one, the voltage is stored in the form of sparks or the so-called electrostatic lines of force. But this one, the voltage is stored by means of chemical reaction. There is no electrostatic lines of force, but it is by chemical means. There is a chemical reaction once the voltage is applied to this capacitor. So this voltage is stored and it is held for a long period of time. Kaya it can be served as a secondary power supply of that UPS unit for the computer system. Okay? These capacitors also are best applicable when it comes to coupling, especially the audio frequency coupling. The frequencies are ranging from 20 Hz to 20 kHz, the sound frequency. Because what is much of a coupling process is 1 microfarad to 10 microfarad. Remember that the lowest capacitance for this is 0.5 microfarad and the maximum is 10,000 microfarad. Compared here, which is 0.5 microfarad and below. So, we cannot use these capacitors for coupling audio frequency. No? They are better applicable when it comes to higher frequencies, radio frequencies. Remember that radio frequencies are ranging from megahertz to super high to gigahertz. From very high frequency, ultra high frequency, and super high frequency used by the cellular phones and satellite communication. Okay? Okay. Those are all about the capacitors. And now let us come to the inductors. We have here inductors. Inductors, like capacitors, will also store voltage, but in the form of magnetic field. Because these capacitors here will store voltage in the form of electrostatic lines of force, but this one by means of magnetic lines of force or the magnetic field. No? Okay. Actually, inductor basically is made of, it is just a coil of wire that may be wrapped or maybe not wrapped around a core. Okay, we have here an example of that. For example, this one. Okay. Okay. It is just a coil of wire. Okay. 1, 2, 3, 4. Any number of turns, as long as it forms a coil. Okay. We have here. Okay. It is a length of wire being formed a coil or inductor. There is no core because as it is said, a coil of wire that may or may not be wrapped around a core. We have here an example of core. We have here an example of core which is inserted inside, or a length of wire is form a coil around this core. A core may be made of powdered core or iron core. Core, by the way, is used to concentrate magnetic fluxes. Naturally, when the current is applied to this inductor, electric current will circulate around the coil and introduces magnetic field. We call it electromagnetism. because the magnetism is created by electricity or current. Naturally, it is called electromagnetism. There is electromagnetism around this coil, no? Then without a course, the magnetic flux or the magnetic field, because magnetic flux is a magnetic lines of force. The entire group, the entire number of magnetic lines of force or the magnetic fluxes are called as magnetic field. Without a core, spread out. Yung magnetic field spread out, no? Spread out. There is no unity. Kumbaga, there is no solid. There is no quantity. It is not solid. Because it is not united. It is spread out, the magnetic field. But with a core, the flux density is very high because the magnetic field is not spread out. Instead, it is compressed. It is so dense. The flux density is so dense, kumbaga, no? And that's why it increases the induction process, and the efficiency of the inductor is increased. The inductance is affected. Remember that inductor has its inductance. Inductance is an electrical amount of inductor. It is measured in Henry, millihenry, and microhenry. For a capacitor, the capacitance is in microfarad, in farad, microfarad, nanofarad, and picofarad. For the resistance of a resistor, it is measured in ohms, kilo ohms, mega ohms, and giga ohms, and probably tera ohms if there is resistors with a resistance of tera ohms, no? Okay. So, core is used to concentrate magnetic fluxes, and it intensify the induction process. So, you will know later on what is this induction, no? Okay. The symbol if this core is inserted is like this. It is like this. This is the coil. And we have here the invisible line. There are two invisible lines signifying or symbolizing the inductor powdered core, because although this is magnetic material, but it is insulator, because when we measure this with this, using multimeter, analog multimeter, or even you use 100 kilo ohms as the maximum, or 10 kilo ohms as the maximum ohmmeter range, infinity, there is no continuity. There is no continuity, meaning it is an insulator. But remember, it is magnetic material, iron, magnetic material. But when it is measured using ohmmeter, it is a conductor. It is an insulator, but both are magnetic materials. Why is it that it is powdered? Because if we will use this one as the core of this, okay, we have here inductor iron core. The symbol is this one. The symbol is this one. If the core is made of iron, okay, once it falls down, it won't break the core. Kaya it is called iron core. But this one, powdered core, once it falls down, we have here powdered core. Once it falls down, it breaks. Meaning to say, it is just a powder of irons, wherein every powder is insulated with varnish. That's why when we measure it with ohmmeter, it is infinity, no continuity. No, it is powdered, in the sense that a powder of iron is being insulated, each of the powders, then compressed and shaped like a bar. No? It is best applicable to higher frequencies because this transformer will process radio frequencies ranging from kilohertz to megahertz. Okay? Unlike this one, for this transformer, it uses iron core because it processes only 60 hertz from the AC power line. No? From the AC power line. Okay. But when it is a coil alone, without a core, the symbol is like this. It is just like this. No? Inductor air core, inductor powder core, inductor iron core. Okay. We have heard the examples of inductor air core. Then, inductor powdered core because it uses ferrite. Ferrite as a powdered core. No? Powdered core. Powdered core. We have here iron core because it uses iron metal. Kaya solid, no? Okay. Also this one here, powdered core. Powdered core also because the core being used here is a powdered core. Now, as what I had said a while ago, that inductors contain inductance in Henry, millihenry, and microhenry. It has inductance. We can actually measure the inductance. Okay, we have here. Let us try to use this coil. Okay. We will try to measure the capacitance of this, the inductance of this inductor air core, no? Using this test instrument. By the way, we are using several test instruments here. We have here an analog multimeter, no? Analog multimeter. Then we have also a digital multimeter. And the last one is another by the way, is LCR, digital meter. L is inductance, C is capacitance, and R is resistance. Meaning to say, this LCR digital meter is designed to measure the inductance in Henry, millihenry, and microhenry. Also, you can set this one to capacitance for measuring the capacitance in farad, microfarad, nanofarad, and picofarad. Also for the resistance, that's why it is LCR. Resistance in kilo ohms, mega ohms, ohms, and giga ohms. No? Okay, this is also a digital multimeter. And of course, we have here an oscilloscope, which is used to display and measure the time varying voltages and currents values, and also measure the frequencies of the AC signal. We have heard the AC signal. Okay? And of course, we have here an equipment, a variac transformer again and again, which will provide different levels of voltages, AC voltages at the output of this variac transformer. Okay. Now, let us measure the capacitance. Oh no, the inductance of this inductor. Say, we will try to make another one. Okay, for an inductor, no? Okay, here we will try to make a coil just like this, because an inductor basically is a coil of wire being wound, or it can be wound, or it can be wrapped, it can be not wrapped using a cord. So again, so we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let us measure the 10, 11, 12. There are 12 turns of this inductor. Then, let us, by the way, this magnet wire is made of copper. It is insulated with electrical harness. There is electrical harness. Let us try to scrape off the surface because it is covered with insulator. It is covered with insulator. So that we can connect the test pads of the multimeter. Just like that. Okay. Okay. Without a core, this is just an inductor air core. We will measure the inductance. Okay, we have here. We will connect this one here using alligator clip. This one. And the other one is this one here. Okay. Then the two alligator's clip will be connected to the two test pads, to the two terminals of the test probes or test probe or test pads or test leads of this LCR meter. Okay, we have here. Now the coil or the inductor air core is connected to this digital meter. We will set the function. It should be microhenry. We have here microhenry as the inductance of inductor, no? Henry. Picofarad capacitance. Mega ohms. We have here mega ohms still. Then Henry. The capacity, no. Here probably it is not connected very well. It should be, that is picofarad for capacitance. Henry. There's something wrong. There's a technical problem with this. Picofarad. Let us try to scrape off the surface. Okay. Probably okay, we have here the inductor air core now. The two terminals of the inductor air core are connected to the two test pads of this digital meter. We are at inductance meter. The inductance now is 2 microhenry. 2 microhenry. Okay. The inductance can be varied by the number of turns. The more the number of turns, probably the higher the inductance. Or it is determined also by the diameter size of the wire. This is gauge number 24. It is thinner. When we use a thicker one, it is around gauge number 20, gauge number 19. We have here this gauge number 19 because the smaller the gauge number, the thicker the wire. It is actually gauge number 19. This one, it is thinner, gauge number, probably this is gauge number 22, but it is thinner. No? The inductance is also in accordance with the thickness, the diameter size of the wire. We will find out which is higher, the thinner or the thicker. Also, it depends upon the number of turns, the circumference, the cross-sectional, not only the diameter size of the wire, but also the cross-sectional area of the coil. Also, if it is compressed, and strengthened or refracted, which is lower in capacitance. Yung stretched or yung compressed na coil. So the inductance will be varied according to those parameters. Okay? So now the inductance is 2.1 microfarad. How about F? Inserted with core. It is 2.1. It is now 13.9 microhenry. The inductance is increased. Meaning to say, the efficiency of the inductor is increased because core compresses the spread out magnetic field. It concentrates magnetic fluxes. No? Okay. Mana siya. So, core naturally will also increase the inductance. Okay. Let us now increase the number of turns. Okay, we will use another inductor to compare the number of turns. We have here 12 turns of this inductor. How about we will increase the inductance by increasing the number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There are 16 turns here. Then we will strip off the surface because it is still covered with insulator. Okay. Okay. We will measure the inductance. A while ago that was smaller inductance. Probably there are connections misconnected. The inductance a while ago using this inductor, that was 2.1 microhenry. But now, the number of turns actually is 12 turns with the same diameter size of the wire, with the same cross-sectional area of the wire. Also with here, but what is changed is actually the number of turns. A while ago, that was 12 turns, but here is 16 turns. The inductance a while ago was 2.1 microfarad, but now it is 2.3 microfarad. 2.3 microfarad. It is increased, no? From 2.1 to 2.3 or 2.2 because the number of turns here is increased with the same diameter size of the wire, with the same cross-sectional area of the wire. So, meaning to say, the more the number of turns of the wire, the higher the inductance. Okay? How about if we will use different gauge number of the wire? So here, we are using now a thicker wire, which is gauge number 19. We have here gauge number 22. I think this is gauge number 22 or 21, which is thinner. Okay? There are actually 16 turns. We will use the same number of turns. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There are 16 turns, okay? So we'll cut this one. strip off the surface because it's still covered with insulator. Okay, then okay, then another in here. It's 2.8 microhenry. 3.1 increased. A while ago that was 2.2 microhenry. Using this wire with the same number of turns, 16 turns, but the diameter size of the wire is thinner, which is gauge number 22. This one, gauge number 13, thicker with the same number of turns, 16. But okay, we are using different gauge number of the wire, which is gauge number 19 compared to here, gauge number 21, but with the same number of turns. Now the inductance is increased. When we are using thicker wire, the inductance increases to 2.5. From 2.2 here, it is increased to 2.5. Meaning to say, thicker wire is better in inductance because the inductance is increased to 2.5 microhenry. Okay. How about if we are going to compress 2.5 microhenry? Compressed, it increased also. No? From 2.5, it is increased to 2.6 once the coil is compressed. But if it is rarefacted, decompressed, the inductance is decreased to 1.8 or 2.1 to 1.8. A while ago, this was 2.3 or 2.5. But once it is spread out, what will happen? The inductance is changed to 2.1. It is decreasing. Compared to compressing, the inductance is higher. It is higher, 2.5. If it is decompressed or rarefact, the inductance is lower. Okay? Okay. So, we were emphasizing only how the inductance is determined. So, there is different inductances with regards to the diameter size of the wire, the circumference area of the wire, the number of turns, it is compressed and rarefacted of the coil, so different inductances. Okay? Then, before induction, because it is said that there is induction of this inductor. What is that induction? Okay. We will try to make another activity here. Okay, we have here. This is an inductor, iron core inductor, because there are 2,000 number of turns of magnet wire with a gauge number of 27. No, it is much thinner compared to this. Much thinner. Then we have also here okay, another inductor wherein the light emitting diode is connected across it. No, these are the two terminals of the inductor. Then we have here a power source. The first inductor is connected to the AC source. Then let us suspend them closer. Okay, you notice that this lid is lighting. or illuminating. Meaning to say that there is induced voltage in this inductor based from the variation of the magnetic field here. Although they are not physically connected, but there is induction. No? Meaning, induction is actually the voltage generated by this inductor by means of magnetic field of the first inductor. No? There is induced voltage here or induced current in this inductor based from the variation of the magnetic field here. Okay? Okay. That was all about induction. Okay, let us now come to the different appearances or several appearances of these inductors. We have here the inductor air core. We have also ceramic molded color-coded inductors, because there are lots of inductors, also color-coded inductors in any electronic circuits. For example, this one here. There is actually one inductor here. One inductor, this one is inductor. No? You can determine that this is inductor because adjacent to this inductor, color-coded inductor, there is mark L3 or L16 yata yan, L16. Meaning to say that this is inductor. Because if it is a resistor, there is a mark R10, R12, just like that, no? Okay, this is inductor. There are also color coding for inductors. So the color coding and the corresponding value can be based also from the color codes of the resistors. Okay. The colors here actually is blue, red, black, and silver. Blue, red, black, and silver. Okay. We will try to translate the color-coded inductor into inductance. We have here blue, red, black, and silver. There are actually 4 colors for this inductor. Black. Okay. Blue is 6, remember? Because the first 2 colors belong to the significant figures. There must be a corresponding value of these first 2 colors. Blue is 6, red is 2. Then, the third color serves as a multiplier, and it is times 1. And the unit is microhenry. Microhenry always. More or less, this is 10%. Okay? So, 62 times 1 as a multiplier is 62 microhenry with a tolerance of more or less 10%. This is now the corresponding inductance of these color-coded inductors. There are usually 4 colors. How do you read the colors or translate into inductance? The same as what we have in resistors also. The color code for the inductors use also the same colors with the same corresponding value of the colors. Okay, also for the tolerances. Now, let us prove how much is the inductance. Okay. We have here. We will use again this inductance meter for measuring the inductance of this inductor. 62.2 microhenry. 62.2 microhenry as a measured inductance. So, we will try if we will prove, no? We will figure out or compute to compare the measured value. So, the measured value actually is 62.2 microhenry. Then, the coded value is 62 microhenry. let us determine if this measured value is still tolerable. Okay, 62 times 0.1, because the tolerance is 10%. So convert it into a decimal number, and it is 0.1 as the corresponding decimal number of that percentile. So this is 6.2, the product. To get the more, so 62 as the coded value plus 0.1 is 62 62 as a coded value plus 6.2 is 68.2 microhenry for the more. And for the less, 62 minus 6.2, this is 8, this is 5, so 65.8 as the minimum permissible deviation of inductance, and the maximum is 68.2. Again, there is a mistake with our computation. I'm sorry. So because 6.2 minus, or 62 minus 6.2 is 55.8. Meaning to say 55.8 microhenry as the minimum permissible deviation. From the coded value, which is 62 microhenry, then the measured value is 62.2. Okay, somewhere here. So it is between 68.2 and 62. So it is 62.2 is much closer to the coded value, meaning to say that the measured value is still good and tolerable since it is within the tolerance limit. Okay? Then we have also here ceramic molded inductors, ferrite bead choke coil, then ferrite core inductors. We have here the symbols. Cement molded inductor. It doesn't use colors. Instead, it's a numerical value. We have here 472. No? So 472 as a numerical value being printed on the surface of the body of this inductor. So the last digit, there are 3 digits. The last digit indicates the number of zeros. So this is 2 zeros. So this means 4,700, and the unit is microhenry always. Microhenry. No? Microhenry. Then when we convert this into Henry or millihenry, because we are always looking for the less number of digits, yung kukunti lang ang number ng digits so that it can accommodate the complicated or the intricate schematic diagram of an electronic device. So, micro is 10 raised to the power of negative 6 and milli is 10 raised to the power of negative 3. The difference is 3. 6 and 3, but the difference or the gap between them is 3. So we are converting actually smaller into larger. Smaller into larger, we have to move decimal point to the left 3 places because the gap between them is 3. So the decimal point is over here after 0. 1, 2, 3. That becomes 4.7 millihenry. This should be the appropriate value that you are going to use since it has less number of digits. Unlike this one, there are 4, whereas this one there are 3 including decimal point. It can only accommodate a little space. Remember that our diagram is very complicated, very miniaturized, and of course the electronic circuits always use the least number of digits of the quantities. For example, for the resistance, for the inductance, for the capacitance. No? Now, we have here the toroidal core, because the core looks the same as a ring. It is also powdered. That's why the symbol is like this. Then there are two toroidals here. This toroidal core inductors is used as a filter tube coil. So an example of that is this one. We have here the toroidal filter tube coil. The purpose of this is to prevent the entrance of the high frequency noises beyond 60 Hz. Remember, the Solico company, because we are in Sorinlete, we are receiving the distributed voltage from the Solico. It is 220 volts with a frequency of 60 Hz. So this low pass filter together with the capacitor will allow only the 60 Hz frequency, the desirable frequency, and bypassing out or filtering out the higher frequency or beyond frequency from 60 Hz toroidal. No, it is usually used or applied in a low voltage power supply circuits or any power supply circuits, even in display panel TV, LCD LED TV. Okay, then we have here a transformer. A transformer, by the way, is composed of two inductors, no? A primary inductor or primary winding, then another inductor or another winding. It composes of two or more inductors because there are two inductors at the output. One inductor here, then two inductors because there are three terminals. It can have also 6 terminals. That's why there are 5 inductors at the output also. There is also a transformer that it is multi-output because it has several inductors at the output. No? Transformer isolation because the two inductors are separated to each other. Whereas this one, auto transformer, because there is only one length of wire being wound. No? It goes like this. So it goes like this. It is just like this. Being wound. Then here. Then another turn. 1, 2, 3. Okay. This could be a primary inductor or primary winding. Then another inductor. There is only one length of wire being wound. Kaya it is called auto, means one or self or one, no? This would serve as the primary inductor. Then secondary. Another terminal here will be connected to serve as the secondary inductor. It goes like that. Because if it is composed of two inductors, this could be the primary. Then another turns for the secondary. Okay? It is just like that. Okay? Okay, just like that, no? The primary and the secondary. Although the secondary rough the layer of the primary, but they are not physically connected because there is an insulator here. This serves as an insulator, the harness that covers the copper wire. Because if we will try to find out whether it is an insulator, use times 10 kilo ohms. Short it is spreads. When you are using ohmmeter, then you have to adjust the 0 ohm adjuster. The deflection pointer should be set to 0 level, 0 ohm, because the 0 ohm is somewhere here. Okay? Now, there is no deflection of pointer, meaning to say, it is insulated with harness. Although they are right, the secondary inductor or winding rides on the primary, but they are not still physically connected. They are actually separated. So we call this one as isolation or separation transformer. But the other one, there's only one continuous coil. The primary and the secondary are physically connected. That is why we have here. Okay. A while ago, we emphasized that inductor will store voltage in the form of magnetic field. And we prove it actually because the variation of magnetic field from this source or from this primary is cutting across to the secondary, no? Just like this. Okay. There's a length of wire here being one, but there's a variation of magnetic field here because this inductor is supplied with AC volts 220. Naturally, there is a very strong magnetic field around this coil. But once it is placed closer, naturally there is induced voltage. We can actually measure the voltage here, no? So we'll try using this one. We'll try to connect here that there is really a voltage. And also, we will connect this digital tester to measure the voltage also. We will set it to, we are using voltmeter and set the type of current which is AC. We have here AC. No, because if it is like that, DC. If it is like that, AC. Because the voltage outputted here is AC. Okay, we will connect. See here again, we will use 2 alligators clip. And connect here. How much would be the voltage outputted? Okay. Okay, look at this one. The voltage induced in the secondary here, in the second inductor, is around, okay, 3 volts. Okay, 3 volts. The induced voltage at the secondary inductor. Then over here, we'll try to check. Okay, that was 3 volts. We have here the AC volts. 3 volts. 3 volts at the AC voltmeter. And also here, try to one, two, three, 4, 5, 6 times 1. Okay, 6, 3. There's something. Okay, we have here the AC waveform at the output of this inductor. No, it is somewhere here. The induced voltage is 3 volts. Okay, that was the AC waveform induced because this transformer actually is supplied with AC volts. Naturally, there is a very strong magnetic field here. Variation of magnetic field. due to the increase, decrease of the current and voltage. Naturally, the magnetic field also will expand, collapse, expand, collapse. It goes like this. We have here one cycle with two alternation, positive and negative alternation. In the first half cycle, naturally, it increases the voltage to 311 as the peak value or 220 as the RMS value. Also with the negative alternation, there is negative 220 volts and negative 311 volts as the peak value. In the first half cycle, it goes like this. We have a coil, then the AC source. This is negative and this is positive during the first half cycle. So the voltage increases to 220 volts, for example, and there is a magnetic field here. The magnetic field is expanding. But once it falls down to zero, the magnetic field collapses. So the magnetic field expands and collapses in accordance with the increase and the decrease of the voltage. Then, after the positive alternation, what comes next is the negative alternation. During the negative alternation, the polarity changes. This is now positive and this is now negative because what follows is the negative alternation. So again, expand once the voltage increases and collapse once the voltage decreases. So there is always a change of polarity because there is no fixed polarity with the AC voltage. There is polarity, but it is not stagnant. No? The polarity reverses 60 times in 1 second, for there are 60 cycles in 1 second. No? So, there is variation of the magnetic field here. Collapse, expand, collapse, expand. And that's the reason why the secondary inductor or the secondary winding induces voltage. The voltage reading here is actually, that was the induced voltage. And the waveform is being shown here. And there is 60 Hz frequency actually. Okay? So, this will constitute as a transformer because a transformer is composed of 2 or more inductors separated to each other for an isolation transformer. No? There is a variation of the magnetic field. That's why the magnetic field from the primary is cutting across to the secondary. And the secondary winding or the secondary inductor induces voltage. And that was the induction. There is a so-called electromagnetic induction because there is magnetism or electromagnetic field because the magnetic field or the magnetism is actually created by current. No? Because if it is not, there is no variation of the magnetic field here, there is no variation of the voltage also here, this inductor will not induce voltage. So we will prove. No, we will prove. Because transformer is an electronic device that transfers electrical energy from the source to the destination. The destination now is this secondary inductor. Okay? So we will prove by using this inductor or using this variac transformer. Using this variac transformer, here we will set this to AC, still AC. We will set this to 9 volts. Okay, 9 volts. Okay, we have here 9 volts. This variac transformer outputted the 9 volts by rotating this rotor shaft. That's why we achieve or we have 9 volts at the output here. So we will connect this one to this transformer from 0 to 9. We have here 0 to 9, no? Okay, 0 to 9. 0 to 9. 0 to 9. We have here 9. Okay. We will be sure if there is an output voltage at the secondary. Okay, we will use another multimeter to measure the output voltage here. Okay. Here. Set this one to AC volts. AC volts, okay, AC. The other one is connected here. If there is really an output, there is 222 volts at the output. The primary is now reversed. We are using 9 volts here, 0, 9. Supposed to be this is the secondary and this is the primary. But we invert the situation. No? The primary winding here, which is 0, 9, is supplied with 9 volts actually from this variac transformer. No? We reduce the voltage from 220 volts from the outlet distributed by the Sulico. We reduce it to 9 volts by using this variac transformer. Actually, there is an induced voltage at the secondary and that is 220 volts. 224 volts. Meaning to say, it is an step-up transformer because the primary is 9 volts but the secondary now is 225 volts. So there is an induction at the secondary. How about if the voltage applied to the primary is DC? DC. We'll try to measure how much is the voltage here. Since it is AC voltmeter, we will press this one to make it DC and measure how much is the voltage over here. This should be the positive side and the negative side. 9 volts, 9 point something. So we will connect that one to the primary. We'll connect that one to the primary to prove if there is a secondary voltage or there is induction at the secondary winding. Primary supplied with DC, fixed polarity. The voltage will not decrease. It is stationary na 9 volts. The 9 volts here being supplied to the primary is stagnant. It won't reduce, it won't increase. Stationary, permanent 9 volts. Now, this should be AC if there is really voltage at the output. So, 0. 0 volt. 0 volt. 0.00. Almost 0. That is practically 0 volt. So, there is no induced at the secondary. Although there is a primary voltage. Because the voltage applied is not varying. It is fixed in polarity kasi. There is fixed current. It goes like this. There is fixed current. Unlike a while ago, it is measured with 0, 9 volts, 0, negative 9 volts. But now, it is supplied with 0, 9 volts. DC. AC. Once it is AC, the magnetic field expand, collapse, expand, collapse, expand, collapse. In accordance with the increase, decrease, increase, decrease. But here, increase is stationary magnetic field. The magnetic field is just stationary. It doesn't collapse nor expands. So naturally, since there is no variation of the magnetic field, there is no induced voltage at the secondary. It is 0. No? Okay. That's the essence of the AC voltage because there is variation of the magnetic field. There is no induced voltage in the coil once the magnetic field is not varying. Variation of magnetic field is made possible only by the AC voltage. Okay. Because mutual inductance. There is mutual inductance once the magnetic field in the primary is cutting across to the secondary. So there is mutual inductance. Meaning to say, there is induced voltage in the secondary because there is variation of the magnetic field. But in this case, the primary is DC volts. There is no variation of the magnetic field. It is stagnant or stationary magnetic field. And stationary magnetic field cannot cut across to the secondary. And that's why there is no induced voltage in the secondary. Okay? Okay, let us now come to the application of this transformer. Isolation transformer, iron core, because the core is made of metal. Then, it is a power transformer because this transformer is used to transform AC voltages. For example, the 220 volts from the outlet is being transformed to a lower voltage at the secondary. So we call it power transformer. But this one, this is not a power transformer. It is actually an audio frequency transformer. Audio frequency. It is used for the audio amplifier that will process the audio frequency 20 Hz to 20 kHz, which is the voice frequency or the frequency of the music or anything that you can hear. They belong to the audio frequency. Okay? Power is the voltage at the outlet which is being transformed. Okay? But we have also here, this transformer is actually found in any TV receiver. For example, we have here switch mode transformer. This is actually a switch mode transformer, no? Switch mode transformers which are used by the TV receiver. Any TV receiver, even in a LED TV receiver, a plasma display panel TV receiver, or even the latest technology, use switch mode transformer. This switch mode power supply is applicable to any electronic circuitry, no? Okay, even the DVD player, it has also a switch mode transformer we have here. So, it is powdered core in the sense that it is not made of metal. Okay? So, it is not a power transformer, it is just a switching transformer. It is a transformer once it is not connected in the circuit. But once it is already connected in the circuit, there is a purpose of that. And the purpose of the transformer is a switching transformer that will provide a regulated voltage at the output despite of the variation at the input of that power supply. Okay? We have here adjustable slug IF transformers, for example, because these transformers are found in an obsolete radio receivers. IF transformer, intermediate frequency. No, the frequencies that they are tuning in is somewhere at 455 kilohertz. If this is an FM IF transformer, they tune in the frequency which is 10.7 megahertz. And we have also here the RF transformer, because this transformer is designed to intercept or receive the radio frequency. For example, of the AM radio receiver, we have 540 kHz for the DYRB. DYHP is 612 kHz. This serves also as an antenna. But specifically, this transformer is a radio frequency transformer because those frequencies, 612 kHz, the radio frequency station of the DYHP, the radio frequency station for the DYRB, 540 kHz, are being intercepted by this RF transformer. Kaya tinatawag na RF transformer. Actually, it is adjustable slug. We can vary the inductance as you move the inductor. No? Also with this transformer, it is not a power transformer. Instead, it is IF, intermediate frequency transformer. We can vary the inductance of this inductor. For example, you have here we are now at millivolt. Okay, let us change it to we have here pala, because this digital meter doesn't have an inductance meter. Only this digital meter is equipped with inductance meter. Okay, so again and again we will use these alligator clips Then connect it here to the terminal of the primary winding, because there is primary and the secondary. It is a powdered core isolation transformer because it composes of two windings separated to each other with invisible line, meaning to say the core being used is powdered core, and there is arrows pointing up and pointing down because we can actually vary in and out the, we have here, there is a slug. It is adjustable slug or the core of the transformer. Okay, we will set this one here. We will set it to inductance using this function selector, no? Okay, we are now at the inductance meter because the unit now is microhenry using this function selector. Then rotate this slug. The inductance now is 425. Then we can change it to 433. Then we can adjust again the inductance to 415, or it varies the inductance as you rotate the slug, as you vary in and out the core. There are coils here. The inductance is varied in accordance with the variation of the slug or the core, no? Okay, that's why it is called variable transformer. It is the inductance which is varied. Here, in this variable transformer, it is the voltage which is varied. It is a power transformer. Actually, this is not a power transformer. Instead, it is an IF transformer, intermediate frequency transformer, and the radio frequency transformer. Okay. We have here also balloon transformer.